Temperature and heat. We want to ask ourselves the question, what's the difference between a hot cup of coffee and a cold cup of coffee? And the answer is not $1.50 at Starbucks. The answer is that in the hot cup of coffee, the molecules are moving faster. They have more energy, they're moving around faster. Temperature tells us how fast those molecules are moving around. Heat is energy transfer between objects. Temperature is a measure of how fast those molecules are moving, the average kinetic energy of the molecules that make up a substance. And I know that in everyday language, we interchange these terms sometimes. And in physics, we have very specific definitions. It's no different from when we learned about velocity or speed, right? In everyday language, we interchange those terms. In physics, we have very precise definitions. And the same with acceleration and things like that. So it's no different. Heat, energy transfer, energy that moves from one object to another because of a temperature difference. Temperature, the average kinetic energy of the molecules that make up a substance. I like to use this analogy. If we're wondering which person, A or B, has more money, we could think of money as being the heat, right? The ability to do some work, the heat, the energy that could be transferred out. In this case, the ability to buy something, right? Which person, A or B, has more money, has the ability to buy something? Person A has $1 in each pocket. That's like a hot object, right? Take something's temperature, it tells us that the molecules are moving fast. In this case, he has a lot of money in each pocket. Person B has a quarter in each pocket. That's like a cold object. Which one has more money? Well, we need a little bit more information, don't we? We need to know how many pockets they have. Person A has 3 pockets. Person B has 16 pockets. So who actually has more money? Person B does. They've got more money because they've got more pockets. So we could convert this exact same scenario into a temperature question. We could say, which object has the ability to burn our skin? A spark from a 4th of July sparkler that's 2,000 degrees, or a hot cup of coffee? Well, the answer is the cup of coffee, right? We've all had one of those sparks land on our skin. Doesn't do too much damage. The reason is it's like person A. The spark is hot, right? The molecules have lots of energy, but there aren't very many molecules in that spark. So the total energy that could be transferred to our skin that could do damage is not very much. But the cup of coffee, each molecule might not be moving anywhere near as fast as the molecules in the spark, right? It's 100 degrees C instead of 2,000 degrees C. The cup of coffee, but there are lots and lots and lots of molecules in a cup of coffee. So the total energy in that cup of coffee is very high, and that spills on you, and it could do a lot of damage. That energy gets transferred to your skin, could do a lot of damage. Maybe that'll help figure out the difference between a temperature and heat. So temperature tells us the energy of each molecule, but you have to know how many molecules there are before you can figure out the total heat available to go into your skin. In that spark, because there were so few molecules, there wasn't a lot of total heat available that could go into your skin and do damage. In the cup of coffee, each molecule didn't have that much energy, but there were so many of them that a large amount of energy was available, a large amount of heat was available to transfer to your skin and do damage. A little bit, maybe that helps you clarify the difference between temperature and heat. Temperature tells us each molecule, what it's doing on average, and heat is sort of the total available. And of course now we need the ability to take temperatures and to quantify this a little bit. So we come up with some useful temperature scales. And here are 3 of the more common ones. You might think that Well, basically, you come up with some numbers that make sense at the time. I'm not sure for Fahrenheit where these numbers came. I've read all kinds of different stories about where the numbers came from for the Fahrenheit scale. I'm not sure I believe any of them, but you can do your own search and figure it out. One story I read was that they didn't want the lowest temperature on Earth to be negative. So they picked 32 degrees to be what water freezes at, and that way the lowest temperature on Earth wouldn't be below zero. But of course, they missed that. We know that we have negative temperatures on Earth on the Fahrenheit scale. And why the boiling point of water is 212, I'm not sure. I heard one story that they were trying to hit 100 degrees for body temperature, human body temperature, but of course they missed that. So I don't think those are true. But anyway, the book had one story that was similar to some of the ones I've read. But the idea is you've got a freezing point for water. That's a very common occurrence, right? So that's one that we think about a lot. And we've got a boiling point for water. That's another very common occurrence that we use a lot, temperature that we use a lot. And most of our everyday experiences happen in between those two. So that's a nice range. That's a nice scale to look at. And on the Fahrenheit scale, we're going from 32 Fahrenheit to 212 between those two points. The Celsius scale makes a little bit more sense. You pick two very common occurrences like water freezing and water boiling. You make one of them 0, one of them 100, and then most of what happens in between is our everyday experiences, our room temperature, our environmental temperatures, body temperature. All of that happens in between there. There's a problem with these two scales. The 0 is set very arbitrarily. And so an example I heard recently would be that if I was the tailor in a small town somewhere, and I needed to be able to measure the height of every person in the town so I could make a suit for every person in the town, I could put a meter stick on the wall. And when I put the meter stick on the wall, as long as the bottom of the meter stick is low enough to capture the height of the shortest person in town, and the top of the meter stick is high enough to capture the tallest person in town, then I could leave my meter stick here. The shortest person in town comes in, I put a height of 0, the tallest person maybe gets a height of 1 meter, I've captured everybody's height in that meter stick. But I might want to know, and that would work perfectly well for me and my business in my town. But at some point, somebody might come into my office and say, I am twice as tall as Johnny, and I want you to make some pants for me. Well, on my scale that's attached to the wall, because I have an arbitrary 0, how do I know who's twice as tall as somebody else? I don't. I have no reference, no absolute 0 reference. So I'd have to know the floor. The floor is, nobody can get shorter than the floor. So if I knew the floor was 0, and I measured up from that, then I would know if somebody was twice as tall as somebody else. And when we're dealing with temperature, it's important to be able to make those kinds of comparisons. That's why the Kelvin scale came along, and that's the one that we use in most of our equations. The Kelvin scale starts at what we call absolute 0. So we're going to talk a little bit about what that means. I already told you temperature measures how fast the molecules are moving around. And everything is made up of atoms and molecules. You and I are made up of atoms and molecules. Your textbook, the seat you're sitting in, the desk you're writing on, atoms and molecules. Those atoms and molecules are always wiggling and moving and vibrating. And temperature tells us how much they're vibrating. The faster they're wiggling and vibrating, the higher the temperature. So we suck some of the heat out of something, cool it down a little bit, they vibrate less. We pull more heat out, they vibrate less. So what do you think is going to happen as we continue to pull heat out? At some point, we're going to get to the point where they're vibrating so little, we pull a little more heat out, and they stop vibrating. And then we can't pull heat out anymore. There's nothing left to extract because heat, the energy, is the kinetic energy of those molecules. When they don't have any more kinetic energy, it's gone, right? We can't pull any more heat out. We can't cool it anymore. We call that absolute zero, where the molecular motion ceases, where the atoms are at rest. So that's as cold as we can make something. That's absolute zero. And that is 0 Kelvin. And as we go up on the Kelvin scale, we get to 273 Kelvin. And that corresponds to 0 degrees Celsius, which is our freezing point of water. And the Celsius and Kelvin scales have the same unit increment. So from boiling to freezing, from freezing to boiling, it's 100 degrees on the Celsius scale. It's also 100 units on the Kelvin scale. So that's nice because a lot of our equations have delta T. And so it doesn't matter then which scale you're using if you're looking at a delta T, because those units have the same division, increment. But this one, you'll notice, is different. When we go from freezing to boiling, we go through 180 degrees Fahrenheit, not 100. So we have to have this conversion. You get a 5/9 or a 9/5 when you're going from one to the other. You can look up the conversion factors in your textbook. But you want to get from Fahrenheit typically into Celsius and then into Kelvin, or vice versa. But these are the scales we typically use, and most of our equations require us to be on the Kelvin scale. So we want to talk a little bit about phase transitions. Phase, when I say what phase is something in, usually we mean solid, liquid, or gas. And it's these phase transitions that are interesting. So going back to our simple view of these molecules holding on to each other and vibrating, if we have a solid, we have those molecules holding on to each other in a very rigid way. And we add a little heat. We heat it up a little bit. We add a little heat. They start wiggling and vibrating a little bit more. We add a little more heat. They vibrate more. At some point, they are vibrating fast enough where they can just barely hold on to each other in this rigid way. We add a little more heat. They try to vibrate more. They break free from each other. But they have a long, loose way of holding on to each other. That's a liquid. So they're vibrating fast enough that they can't hold on to each other in this rigid way. They've broken free from each other. But they have a long, loose way of holding on to each other. That's a liquid. We add more heat. They vibrate faster, wiggle faster, move faster. At some point, they're going so fast, we add a little more energy, and they have enough energy to break free from each other. They can't hold on to each other at all. They are independent of each other. That's a gas. The molecules are completely independent of each other. They whiz by each other in the room or whatever container they're in so fast they can't grab onto each other. Going back in the other direction, you pull a little heat out of that. You slow those molecules down a little bit. Eventually they are going so slow, as they go by each other, they can grab onto each other. We call that condensation, right? When a gas turns into a liquid. And usually it occurs on a cold surface. Maybe you have a glass of ice water sitting on the table. What happens? The molecules in the air, in this case it would be water molecules, the moisture in the air, normally they whiz by each other so fast they can't grab onto each other. But they hit, a couple of them hit the glass. The glass is cold. They give up some of their energy to the glass. They're moving slower. They can grab onto each other and form a water droplet. And that's what happens on the surface of the cold glass or a cold object. Maybe it's your window in the morning when you take a shower. You get that condensation on the inside. So going down, we're taking energy out. We have a liquid. We've gotten it to condense into a liquid. We pull more energy out. The molecules vibrate less and less as we bring the temperature down. And at some point, they're vibrating slow enough that they can grab onto each other in a rigid way. That's a solid. And then we can keep extracting heat and getting them to vibrate less and less until you get down to absolute zero. I like to use this. I went into my kid's classroom when he was in kindergarten. And I thought, oh, this is going to be fun. I'm going to bring liquid nitrogen in, do some demonstrations for the kindergartners. And I went over, I thought of a little story I could tell them that would get them to understand this. And I practiced on my son, and he got it, and I figured this was great. And I went in there, and I said, when you kids are out on the playground, some of you are running around really fast, and some of you are standing still talking to each other. Who has more energy? And the kids all raised their hand. And, oh, call me, call me. And I picked on some kid, and he said, I can run really fast. Thank God I don't teach kindergarten, I guess is the moral of that story. But I continued. I didn't let that faze me. I continued with my analogy. And I said, of course, it's the kids that are running around fast that have more energy. And I said, and who gets hotter? The kids that are running around fast. And who takes up more space on the playground? The kids that are running around. And it's the same with atoms and molecules. The hot ones are moving faster, they have more energy, and almost universally, there's always an exception, we'll talk about that, almost universally, things take up more space as we heat them up. We call that thermal expansion because the atoms and molecules are vibrating, they're moving around more and more, and they're bumping into each other harder, and they need more elbow space, they need more elbow room. It's like putting a bunch of people on a dance floor, putting the music real softly. We can fit a lot of people on the dance floor. You crank up the music and they start waving their arms and jumping around, and they take up more space, don't they? Same with atoms and molecules. Let's take a look, see if we can demonstrate some thermal expansion.